The Nile was a playground, calm, predictable, forgiving, a river that the Egyptians had been reading since before their civilization had a name, whose floods and whose currents and whose seasonal moods they knew as well as they knew their own heartbeats. But the Red Sea was something else entirely. Volatile, unpredictable, deep in ways that the Nile never was. A body of water that did not forgive mistakes, that did not offer second chances, that swallowed ships and the men inside them with the same indifference that the desert swallowed travelers who did not know its rules. And the Egyptians decided to sail it anyway. Not in small boats, not on short trips close to the shore, but on deep water voyages to a place they called Punt, a land so far away and so rich in things Egypt needed that the journey was worth the risk, worth the preparation, worth the extraordinary engineering achievement that made the whole thing possible. That engineering achievement is what tonight's story is about. The mortise-and-tenon joints, sewn together with miles of rope, that held a ship together under the crushing weight of Punt's treasures. Gold and ebony and live incense trees brought back across one of the most volatile maritime corridors in the ancient world. Because one wrong knot meant total destruction in the deep, unforgiving blue. Before we go any further, subscribe right now if you have not already, hit that bell, and drop in the comments where in the world you are listening from tonight. Now, dim the lights, get comfortable, and let us go to the Red Sea. Segment 1. The sea Egypt was never supposed to sail. There's a reason that most people, when they think of ancient Egypt and water, think of the Nile. The Nile was everything. The source of agricultural abundance, the highway of commerce, the sacred artery around which the entire civilization organized itself, the body of water that the Egyptian people had been in relationship with for so long and so completely that their understanding of it was practically encoded in their DNA, passed from generation to generation through thousands of years of accumulated practical experience. Egyptian boats on the Nile were extraordinary, beautifully designed, expertly built, perfectly calibrated to the specific conditions of river navigation, capable of moving enormous quantities of stone and grain and people up and down the length of the country with a reliability and an efficiency that was the envy of the ancient world. But the Nile, for all its importance, was a river, and rivers, however powerful and however consequential, are fundamentally different from open water in ways that matter enormously for the specific challenge of shipbuilding and navigation, ways that made the skills and the designs and the accumulated knowledge of Egyptian river navigation both relevant and deeply insufficient for the specific demands of Red Sea seafaring. Understanding this difference, understanding exactly what the Red Sea demanded that the Nile did not, and why those demands require the specific engineering solutions that the Egyptians developed, is the foundation on which tonight's entire story rests. The Red Sea is a body of water of genuinely unusual character, shaped by the specific geography and the specific climate of the region in ways that make it one of the more challenging maritime environments in the world for ancient seafarers. It is long and narrow, approximately 1,900 kilometers from its northern tip of the Sinai Peninsula to its southern opening at the Bab el-Mandeb Strait, and nowhere more than about 355 kilometers wide. And this elongated, enclosed shape has specific consequences for the behavior of its winds and its waves that sailors who knew only open ocean conditions or river conditions would find genuinely surprising. The prevailing winds in the Red Sea are not consistent in the way that the trade winds of the open oceans are consistent. They are organized by the elongated shape of the sea into a pattern that is more complex and more demanding than most ancient maritime environments. In the northern section of the Red Sea, the prevailing winds blow from the north or northwest for most of the year, making southward journeys toward Punt, toward the African coast, toward the southern end of the sea, relatively straightforward, while making return journeys against these winds genuinely difficult and requiring specific sailing strategies that the simple square-rig sails of most ancient vessels could not easily execute. In the southern section of the sea, the pattern reverses seasonally. The monsoon system that dominates the Indian Ocean extends its influence into the southern Red Sea, producing a period of southerly winds during the summer months that could actually assist northward return voyages if the timing of the expedition was correctly calculated. This wind system, complex, seasonal, organized by geography in ways that required specific knowledge to exploit, was one of the primary challenges that Egyptian maritime technology needed to address, and the specific sail design that the Egyptians developed for Red Sea navigation was a direct response to the specific demands of these winds. The waves of the Red Sea add another layer of difficulty that Nile-experienced shipbuilders and sailors would have found genuinely alarming on their first encounters with open water. The Nile's waves, even in the strongest winds, are relatively modest. The river's width limits the fetch, the distance over which wind can act on water to build up wave height. And the result is that even rough conditions on the Nile produce waves that are manageable for boats designed for river navigation. The Red Sea is different. Its length means that winds blowing along its axis have a significant fetch, enough to build up wave heights that are genuinely challenging for small and medium-sized vessels, enough to produce the kind of sea conditions that require specifically ocean-going hull designs to handle safely. And the Red Sea has a specific additional characteristic that makes its wave conditions more demanding than its size alone would suggest. Its water is extraordinarily dense, significantly saltier than the open ocean because of the high evaporation rate in the hot, dry climate of the surrounding desert and the limited freshwater input from rivers. And this density affects the behavior of waves in ways that experienced seafarers learn to account for, but that can be genuinely surprising to those encountering it for the first time. The Egyptian ships that would eventually sail these waters needed to be designed from the beginning with these specific conditions in mind, needed to be able to handle the wave heights and the wave patterns of the Red Sea without the structural flexibility that was acceptable in a river vessel but genuinely dangerous in open water. There is one more dimension of the Red Sea challenge that needs to be understood before we can fully appreciate the engineering achievement of the Egyptian shipbuilders: the specific challenge of coral. The Red Sea is one of the most coral-rich bodies of water in the world, its shallow coastal waters and its offshore reefs forming an extraordinarily complex and extraordinarily beautiful underwater landscape that is, from the perspective of a sailor trying to navigate it, an extraordinarily dangerous obstacle course. The reefs in the shallow areas are not all charted, not all predictable, not all visible from the surface in conditions that ancient sailors would have encountered, and a ship that struck a reef at sea, far from shore, in conditions where rescue was not possible, was a ship that was likely lost along with its crew and its cargo. The navigation challenge of the Red Sea was therefore not simply a matter of finding the wind and managing the waves. It was also a matter of knowing the specific geography of the underwater landscape in enough detail to avoid the specific hazards that could destroy a ship without warning, in conditions where the consequences of getting it wrong were total and irreversible. The Egyptians accumulated this navigational knowledge over centuries of Red Sea experience, building up the specific, locally grounded understanding of which routes were safe and which were dangerous, which seasons were navigable and which were not, which landmarks corresponded to which underwater features. And this accumulated knowledge was as essential to the success of the Punt expeditions as any aspect of the ship design. Against this background, the complex winds, the challenging waves, the coral hazards, the specific demands of open water navigation that was so fundamentally different from the river conditions that Egyptian maritime technology had been developed to address, the achievement of the Egyptian shipbuilders becomes genuinely impressive. They did not have access to the long maritime traditions of the Phoenicians or the later Greeks, did not have centuries of open water seafaring experience to draw on, did not have the specific accumulated knowledge of ocean conditions that seafaring peoples developed through generations of exposure to the sea. What they had was extraordinary engineering intelligence, the specific problem-solving capability that had already produced the pyramids and the great temples and the sophisticated irrigation systems of the Nile Valley applied now to a completely different set of physical challenges in a completely different environmental context. And what they produced, the specific ship designs and the specific construction techniques and the specific sailing strategies that made the Punt expeditions possible, was genuinely innovative, genuinely suited to the specific demands of the environment it was designed for, and genuinely influential on the subsequent development of maritime technology in the region. The earliest evidence of Egyptian Red Sea seafaring comes from the site of Wadi el-Jaf on the western coast of the Red Sea, approximately 180 kilometers south of Suez, a site that was discovered and excavated in the early 2010s and that has transformed our understanding of how early and how sophisticated Egyptian Red Sea activity actually was. Wadi el-Jaf contains the remains of what is currently the oldest known harbor in the world, a harbor that dates to the reign of the pharaoh Khufu, the builder of the Great Pyramid, in approximately 2600 BCE, making it contemporaneous with one of the most famous construction projects in human history, and suggesting that the logistical and engineering sophistication that produced the pyramid was being applied simultaneously to the challenge of Red Sea navigation. The site contains the remains of storage galleries, long, narrow tunnels cut into the rock of the coastal cliff face, that were used to store the dismantled components of ships during the periods when the harbor was not in use, protecting the cedar timber and the rope and the other materials from the deteriorating effect of the desert climate and the salt air. This storage system is itself significant evidence of the specific character of Egyptian Red Sea shipbuilding. The ships were not permanent fixtures of the harbor, not kept in the water year-round as ships in a permanent naval installation would be, but were assembled for specific voyages and then disassembled and stored until the next expedition required them. This practice of assembly and disassembly was not simply a matter of convenience. It was a fundamental feature of the Egyptian Red Sea maritime system, driven by the specific logistical challenge of getting ships to the Red Sea coast in the first place, a challenge that was in some ways as demanding as the sea voyage itself. Because the Red Sea coast of Egypt is not easily accessible from the Nile Valley. Between the Nile and the Red Sea lies the Eastern Desert, a landscape of rugged hills and wadis and extreme heat that presented a formidable obstacle to the movement of anything heavy between the two bodies of water, let alone the enormous timbers and the heavy equipment required to build and equip ocean-going vessels. The Egyptians solved this problem in the most direct possible way. They did not try to build ships on the Red Sea coast using materials transported across the desert in assembled form. They transported the materials in pieces and assembled them at the coast, using the disassembly and reassembly capability that the specific design of their ships made possible. This solution required a road, a maintained, organized route across the eastern desert along which the ship components, the supplies, and the labor force required for the expedition could be moved with sufficient efficiency to make the whole system viable. The road that served the Wadi el-Jaf harbor ran approximately 110 kilometers from the eastern branch of the Nile to the coast, across terrain that challenged even modern transportation infrastructure, and its maintenance and its use were organized with the same logistical sophistication that characterized every other large-scale project that Egyptian state administration undertook. The papyri found at Wadi el-Jaf, the oldest papyri ever discovered, dating to the reign of Khufu, contained the journal of an official named Mir, who recorded in detail the activities of his work team as they transported limestone blocks from the Chura quarry to the Great Pyramid construction site, and whose records incidentally illuminate the broader logistical system within which the Red Sea operations were embedded. These papyri are extraordinary documents, the voice of a specific person, doing specific work, in the specific world of the 4th dynasty Egyptian state, and they make the logistical achievement of the pyramid age tangible in a way that the monuments themselves, impressive as they are, cannot quite convey. The same organizational capability that moved millions of stone blocks to build the Great Pyramid was also moving ship components across the eastern desert to the Red Sea coast. And the combination of these two extraordinary logistical achievements in the same reign, under the same administrative system, is one of the most remarkable demonstrations of the organizational capacity of the Old Kingdom Egyptian state. Let your body settle into the comfortable weight of a body that has been still for a while, and let the Red Sea settle into your imagination, its complex winds and its challenging waves and its coral reefs and its extraordinary density, and the specific challenge it presented to a civilization whose maritime experience had been built entirely on the very different conditions of the Nile. The Egyptian shipbuilders who faced this challenge were not intimidated by it. They were problem solvers, the inheritors of a tradition of engineering achievement that had already produced things that seemed impossible, and the Red Sea was simply the next impossible thing that needed to be solved. And they solved it in ways that were genuinely innovative, genuinely effective, and genuinely worth understanding in their full engineering detail, which is exactly where tonight's story is going next. Let your breathing slow, and let the story carry you forward into the specific details of how they did it. Segment 2, The Engineering Miracle, Cedar, Rope, and the Sewn Hull. There's a moment in the history of any engineering tradition when the people working within it encounter a problem that their existing solutions cannot solve, a moment when familiar toolkit runs out, when the techniques that have worked perfectly in every previous context are simply not adequate to the specific demands of the new challenge, and when the only path forward is genuine innovation, the development of something that has not existed before. For Egyptian shipbuilders, that moment was the Red Sea, the boats that had served them so well on the Nile, the papyrus reed boats of the earliest periods, the wooden river craft that developed from them, the elegant barges that moved obelisks and stone blocks and grain up and down the length of the country. All of these were designed for conditions that the Red Sea did not offer and would not offer, and their structural characteristics, perfectly suited to calm river water, were genuinely inadequate for the specific stresses of open water. Navigation. The problem was not simply one of size, not simply a matter of building bigger versions of the same basic design, and expecting the bigger version to handle conditions that the smaller one could not. The problem was structural, a fundamental question about how a wooden hull could be made strong enough to handle the dynamic, multidirectional stresses of open water without the rigid internal framework that later shipbuilding traditions would develop, but that Egyptian technology of this period had not yet arrived at. The solution they found was one of the most elegant and most effective in the entire history of ancient engineering. The cedar question, where the wood came from and why it mattered. Before we can understand how Egyptian ships were built, we need to understand what they were built from, because the specific material choices that Egyptian shipbuilders made were not arbitrary or simply the result of using whatever was locally available. They were deliberate, informed decisions made by people who understood the specific properties of different materials and who went to considerable effort and expense to obtain the specific materials that their designs required. Egypt is not a country of forests. The Nile Valley and the Delta support agriculture of extraordinary productivity, but they do not support the kind of large-scale timber production that shipbuilding requires. The trees that grow along the Nile are useful for many purposes, but not for the construction of large, structurally demanding ocean-going vessels. The Egyptians knew this in the earliest periods of their civilization, and they established trade relationships specifically aimed at obtaining the timber they needed from the places where it grew, most importantly, from the forests of Lebanon, where the cedar trees that were among the most prized shipbuilding materials in the ancient world grew in abundance on the slopes of the mountains behind the Phoenician coast. Lebanese cedar, Cedrus libani, was not simply a convenient local resource that happened to be available for Egyptian shipbuilders to use. It was a specifically sought, specifically valued, specifically traded commodity, obtained through trade relationships that Egyptian rulers maintained with the Levantine coast for millennia, relationships that were important enough to appear repeatedly in the official records of Egyptian foreign policy and commercial activity. The specific properties of cedar that made it so valuable for shipbuilding were well understood by the people who worked with it. Its exceptional strength-to-weight ratio, its natural resistance to rot and to the boring organisms that destroy wooden ships in tropical and semi-tropical waters, its ability to be worked into long, straight planks that were essential for the specific construction technique that Egyptian Red Sea shipbuilding required. The transport of cedar timber from Lebanon to Egypt, by sea along the Mediterranean coast, up the Nile, and then across the eastern desert to the Red Sea coast, was itself a logistical achievement of considerable complexity, adding another layer to the already extraordinary organizational challenge of the Punt expeditions. But the Egyptians maintained their supply chain consistently across centuries of Red Sea activity because the cedar was essential, not interchangeable with any locally available alternative, not replaceable with a material that was easier to obtain. The ships that sailed to Punt were built from the best available material for the purpose, obtained from the source that provided it regardless of the distance and the cost, because the Egyptians understood that the alternative, building ocean-going vessels from inferior materials to save the expense of importing cedar, was not economy but false economy, a saving that will be paid for in catastrophic losses at sea. The mortise-and-tenon joint, Egypt's structural revolution, the central engineering innovation of Egyptian Red Sea shipbuilding, the specific technique that made it possible to build wooden hulls strong enough to handle open water conditions without the internal framework of ribs and keel that later Western shipbuilding traditions would develop, was the mortise-and-tenon joint. This joint, a connection between two pieces of wood in which a projecting tongue of wood on one piece, called the tenon, fits precisely into a matching cavity cut into the other piece, called the mortise, is not in itself an Egyptian invention. It appears in woodworking traditions across the ancient world, and its mechanical logic is straightforward enough that independent invention in multiple locations is entirely plausible. What was specifically Egyptian and specifically innovative in the context of Red Sea shipbuilding was the scale and the systematic application of this joint to the construction of ship hulls, the specific way in which mortise-and-tenon connections were used not just occasionally or in specific structural elements, but throughout the entire hull, creating a system of interlocking wooden connections that gave a hull its structural integrity in the absence of the internal skeleton that later traditions would rely on. The Egyptian hull construction technique, known in the academic literature as shell-first construction, because the outer shell of the hull was built first and the structural integrity of the vessel derived from the shell itself rather than from an internal framework, was a specific context in which the mortise-and-tenon joint became the revolutionary technology that it was. In shell-first construction, the planks of the hull are connected to each other edge to edge, each plank mortise and tenon to its neighbors in a continuous series of interlocking connections that run the full length of the hull, creating a structure in which the strength of the whole is distributed across the thousands of individual connections rather than concentrated in a small number of large structural members. This distribution of structural load is actually a sophisticated engineering principle. It means that the failure of any individual connection, while weakening the structure locally, does not immediately compromise the integrity of the whole in a way that the failure of a central structural member would in a framework-based design. The whole was, in a sense, fault-tolerant, capable of absorbing local damage without catastrophic structural failure, as long as the overall system of connections remains efficiently intact. For ocean voyaging, where the stresses on the hull were continuous, variable, and impossible to fully predict, this fault tolerance was a genuinely valuable property, and the Egyptian shipbuilders who developed and refined the shell-first mortise-and-tenon system were, whether they articulated it in these terms or not, responding to exactly this requirement. The rope, miles of it, and why it was essential. The mortise-and-tenon joints gave the Egyptian hull its basic structural integrity, the connection of plank to plank that created the shell from which the vessel's strength derived. But the mortise-and-tenon system alone was not sufficient for the specific demands of Red Sea navigation, and the Egyptian shipbuilders understood this. Open water exerts dynamic stresses on a hull that go beyond the static load bearing that the joints were designed to handle. The twisting and flexing forces that waves impose on the ship's structure, the way that a hull moving through open water is constantly being pulled and pushed in multiple directions simultaneously, requiring a structural system that can accommodate this dynamic loading without the joints failing under repeated stress. The solution that Egyptian shipbuilders developed for this specific challenge was a rope, miles and miles of it, woven from papyrus fiber or from other plant materials, used in a specific structural application that is one of the most distinctive features of ancient Egyptian ship construction. The rope was used to create what modern engineers would call a hogging truss, a tensioning system that ran the length of the hull, connecting bow to stern through a series of rope loops that passed over vertical supports amidships and pulled the end of the hull upward against the tendency of the hull's own weight to cause it to sag in the middle. This hogging was a genuine structural problem for long wooden hulls in the ancient world. The weight of the hull itself and the weight of the cargo it carried tended to cause the middle of the hull to drop relative to the ends, creating a condition that placed the upper part of the hull under compression and the lower part under tension. Stresses of the wood and the joints could handle to a degree, but that would eventually cause structural failure in a hull that was not specifically designed to manage them. The rope truss managed this problem elegantly and effectively. By pulling the ends of the hull upward, it counteracted the hogging tendency, distributing the structural loads in a way that kept the hull in the shape it needed to be in to function as a watertight, structurally sound vessel. But the rope did more than simply manage the hogging problem. In the specific conditions of Red Sea navigation, the short, steep waves of the enclosed seas fetch and its density produce, the dynamic loading that these waves impose on the hull. The rope's elasticity was a structural asset, allowing the hull to flex slightly in response to wave action rather than transmitting the full force of the impact to the rigid mortise-and-tenon joints. A purely rigid structure, subjected to the repeated dynamic loading of open water wave action, would eventually fatigue at its weakest point. The joints would loosen, the planks would separate, the watertight integrity of the hull would be compromised. A structure with controlled flexibility, stiff enough to maintain its shape under normal loading, but capable of absorbing dynamic loads through slight flexion rather than rigid resistance, was more durable and exacted the conditions that the Red Sea imposed. The rope truss provided this controlled flexibility, and the Egyptian shipbuilders who developed it were, whether consciously or through the accumulated practical wisdom of trial and error and accumulated experience, arriving at a genuinely sophisticated structural solution to a genuinely difficult engineering problem. The sewn hull, when the rope became the structure. The mortise-and-tenon joints and the rope truss were the primary structural innovations of Egyptian Red Sea shipbuilding. But they were not the only application of rope to the ship structure, and the other application is in some ways even more remarkable, because it represents a completely different approach to the structural problem of connecting hull planks that is genuinely distinct from any Western shipbuilding tradition. The sewn hull. In the sewn hull technique, which appears in Egyptian shipbuilding and in various other ancient maritime traditions around the Indian Ocean and the Red Sea, the planks of the hull are connected to each other not only by the mortise-and-tenon joints, but also by rope stitching. Lengths of rope or cord pass through holes drilled in the edges of adjacent planks and tied in specific patterns that both connect the planks and provide the controlled flexibility that open water navigation required. The stitching ran both along the edges of the planks, connecting adjacent strakes in the continuous seam that ran the length of the hull, and through the hull itself, in specific patterns that added structural integrity to the shell in ways that the mortise-and-tenon joints alone could not provide. The specific stitching patterns used in Egyptian sewn hulls are not fully documented in the surviving evidence, The organic materials from which they were made have not survived the millennia in most cases, and the reconstruction of the technique depends on a combination of the surviving physical evidence, the ancient depictions of ships in tomb paintings and reliefs, and the comparative evidence from other ancient sewn hull traditions that are better documented. But the general principle is clear, and its engineering logic is consistent with everything else we know about the Egyptian approach to the structural challenge of open water shipbuilding, the use of flexible connections to distribute structural loads across the hull in ways that allowed it to absorb dynamic stresses without catastrophic failure. A sewn hull flexes, not dramatically, not in ways that compromise its watertight integrity under normal conditions, but enough to absorb the kind of dynamic loading that waves impose on the ship's structure, enough to give the hull the fault tolerance that made it capable of surviving the conditions of the Red Sea voyage. The caulking that made the sewn hull watertight was applied to the seams between the planks, mixtures of plant fiber and natural resins that expanded when wet to seal the gaps between the planks, and the maintenance of this caulking was one of the ongoing responsibilities of the ship's crew during the voyage, checking the seams regularly and recaulking any areas where the seal was compromised. The specific ships of the Punt expeditions. The physical evidence of the specific ship's use in the Punt expeditions comes from several sources. The reliefs carved on the walls of the temple of Hatshepsut at Deir el-Bahri, which provide the most detailed depictions of Egyptian Red Sea vessels available. The fragments of actual ship timber found at Red Sea harbor sites, including Wadi el-Jarf and Ain Sukna, and the papyri that document the organization and logistics of specific expeditions. From these sources, a reasonably detailed picture of the Punt expedition vessels can be reconstructed, not with the precision of a modern technical drawing, but with enough specificity to understand the essential design features and their engineering logic. The ships were large by ancient standards. The Hatshepsut relief suggests vessels of approximately 25 to 30 meters in length, with a beam of perhaps 7 to 8 meters, carrying a crew of approximately 210 men organized into specific functional roles: rowers, sailors, officers, and the various specialists required for specific tasks of the expedition. The hull was flat-bottomed by later standards, not the deep keel design that later ocean-going vessels would develop, but a relatively shallow hull profile suited to the specific conditions of Red Sea navigation, where the ability to operate in relatively shallow coastal waters was as important as the ability to handle open water conditions. The single large sail, a wide, rectangular sail suspended from a bipod mast, the two legs of which spread apart at the base to provide stability without the need for a keel-mounted mast step, was a primary source of propulsion, supplemented by oars when the wind conditions required it. The bipod mast is itself a specifically Egyptian innovation, and its engineering logic is directly connected to the shell-first construction of the hull. A single mast requires a strong keel to absorb the compressive forces it transmits to the hull, but the Egyptian hull had no keel in the conventional sense, and the bipod mast distributed the mast load across a wider area of the hull in a way that the shell construction could handle. Everything about the design was integrated, each specific feature responding to the specific constraints imposed by the others, each innovation necessitated by the combination of the specific structural approach and the specific environmental demands of the Red Sea. The engineering miracle of the Egyptian Red Sea ship was not any single innovation in isolation. It was a specific combination of the cedar timber and the mortise-and-tenon joints and the rope truss and the sewn hull and the bipod mast and the wide rectangular sail, all working together as an integrated system whose whole was greater than the sum of its parts. A system designed, tested, refined, and ultimately proven by the specific, demanding, unforgiving test of the Red Sea itself, a test of the Egyptians passed repeatedly over more than 1,000 years of expedition activity, bringing back from Punt the treasures that furnished the temples and the palaces of one of the greatest civilizations in human history. Let your body find its comfortable weight now, and let the engineering settle into you. The cedar and the rope and the joints and the sail, all of it working together in the dark of the Red Sea night, carrying Egyptian sailors toward a destination that their civilization needed and their engineering made possible. There is more ahead. The route itself, the crossing of the eastern desert, the logistics of the voyage, and the extraordinary cargo that made all the risk worth taking. Let your breathing slow, and let the story carry you forward. Segment 3. The route, carrying ships across a desert. There's a logistical challenge at the heart of the Egyptian Red Sea expeditions that is, in its own way, as impressive as the shipbuilding technology itself, a challenge so fundamental and so demanding that solving it was a prerequisite for everything else. The problem that had to be answered before the first plank of cedar was shaped or the first length of rope was twisted. How do you get a ship to a sea that is separated from your country by a desert? Not a narrow strip of desert, not a short crossing that could be managed with a few days of difficult travel, but the eastern desert of Egypt, a landscape of rugged sandstone hills and deep wadis and extreme heat and almost no water, stretching for more than 100 kilometers between the Nile Valley and the Red Sea coast, offering no easy passage, no natural highway, no route that did not demand extraordinary organizational effort to make viable. The answer that the Egyptians developed, the specific system through which they moved ships and ship components and supplies and labor across this hostile landscape, is one of the most remarkable logistical achievements in the ancient world, and understanding it in its full complexity is essential for understanding how the Punt expeditions were actually possible. The Eastern Desert, understanding the obstacle. The eastern desert of Egypt is not simply empty space between the Nile and the Red Sea. It is a specific landscape with specific characteristics that shape the specific routes and the specific logistics that the Egyptians developed for crossing it, a landscape of considerable geological complexity, its surface divided by the drainage patterns of the ancient wadis into a system of valleys and ridges that offer both obstacles and opportunities to the planners of the expedition routes. The wadis, the dry riverbed that cut through the desert landscape, carved by the occasional flash floods that are the eastern desert's primary form of precipitation, were the natural highways of the desert, their relatively flat floors and their tendency to run in consistent directions making them the most practical routes through terrain that was otherwise extremely difficult to traverse with heavy loads. The specific wadi system that connected the Nile Valley to the Red Sea coast and the area used by the Egyptian expeditions had been understood and mapped in the practical sense of accumulated route knowledge rather than in the formal cartographic sense, over centuries of desert travel, by miners seeking the gold and copper deposits that the eastern desert contained, by quarrying expeditions seeking the specific stone types that the desert's geology offered, and eventually by the expedition, planners who needed to move ship components from the Nile to the coast. The route from the Nile to Wadi El Jaf ran approximately 110 kilometers through this wadi system, and its maintenance and its use were organized as a state enterprise of considerable complexity, involving construction and maintenance of way stations where water and supplies could be cached for the use of expedition teams, the organization of the labor force required to move heavy loads across difficult terrain, and the management of the donkey trains and human porters that provided the actual transportation capacity. Water was a critical constraint. The eastern desert is genuinely arid. Rainfall is rare, unpredictable, and when it comes as a flash flood that carved the wadis rather than as a steady, dependable precipitation that supports permanent water sources. The wells and the cisterns that the Egyptian state maintained along the desert routes were not natural features of the landscape. They were constructed and maintained infrastructure, investments of labor and organization that were as essential to the success of the expeditions as any aspect of the ships themselves. A team of workers moving heavy ship components across 110 kilometers of desert needed water at regular intervals, and if the water sources along the route failed or were inadequate, the entire operation was in danger, not from any external threat, but from the simple biological reality that human beings cannot work effectively in extreme heat without adequate hydration. The logistical planning that ensured water availability along the route was therefore one of the most critical aspects of expedition preparation, and the officials responsible for it were among the most important members of the expedition's organizational team. Carrying ships in pieces, the modular design solution, the specific engineering feature of Egyptian Red Sea ships that made the Eastern Desert crossing possible was their modular design. The fact that the ships could be disassembled into components that were individually manageable, transported separately across the desert, and then reassembled at the coast into a seaworthy vessel. This modularity was not simply a convenience that happened to be available as a byproduct of the shell-first construction technique. It was almost certainly a deliberate design feature, a conscious decision by the Egyptian shipbuilders to make their vessels capable of the disassembly and reassembly that the specific logistics of Red Sea access required. The shell-first mortise-and-tenon construction lent itself naturally to this modularity, because the hull was built from individual planks connected by individual joints. It could in principle be disassembled by reversing construction process, removing the rope lashings and the caulking and separating the planks at their mortise-and-tenon connections, reducing the complete hull to a collection of individual planks that could be transported separately. The specific dimensions of the planks, their length, their width, their weight, were therefore constrained not just by the structural requirements of the finished hull, but also by the transportation requirements of the desert crossing, the need to produce planks that were manageable by the available transportation means across the specific terrain of the Eastern Desert route. A plank that was too long or too heavy to be carried by the available number of porters or loaded onto a donkey could not be transported, regardless of its structural advantages, and the shipbuilders who designed the Punt expedition vessels were working within these transportation constraints as well as the structural and hydrodynamic constraints that the sea voyage imposed. The mast and the sail and the rigging, the upper works of the vessel that were as essential to its function as the hull itself, were also designed for disassembly and transport. The bipod mast capable of being broken down into its component sections, the sail and the rigging rolled and bundled into manageable packages, the various fittings and hardware organized for transport in the same systematic way as the hull components. The storage galleries at Wadi El Jaf, the long, narrow tunnels cut into the cliff face that we discussed in the first segment, were designed to receive these disassembled components and protect them between expeditions, their dimensions and their organization reflecting the specific sizes and shapes of the ship components they were built to store. The fact that these storage facilities existed, that the Egyptians built permanent infrastructure specifically for the storage of disassembled ship components, tells us that the Red Sea expeditions were not one-time events but regular, repeated activities, organized with enough consistency that permanent infrastructure was worth the investment. The workers, who crossed the desert and what it cost them. The logistical achievement of crossing the Eastern Desert with ship components was ultimately a human achievement, accomplished not by machines or by animals alone, but by the physical labor of the men and women who carried and dragged and organized a movement of thousands of kilograms of cedar timber and rope and equipment across more than 100 kilometers of hostile terrain. The papyri found at Wadi El Jaf give us the closest thing available to a first-hand account of what this labor actually involved. The Journal of Mir and his team provide specific details about the organization of work gangs, the daily distances covered, the specific tasks performed, and the conditions under which the work was done. The work teams were organized into named units with specific leaders, the same organizational structure that the pyramid construction employed, the same system of named gangs with specific responsibilities and specific accountabilities that the Egyptian state had developed into one of the most effective labor management systems in the ancient world. Each gang was responsible for a specific section of the transportation task, moving specific component from a specific starting point to a specific destination, maintaining the pace and the organization that the overall expedition timeline required. The physical demands of this work were genuinely extreme. Moving heavy cedar planks across desert terrain in Egyptian summer temperatures, which regularly exceed 40 degrees Celsius in the eastern desert, required sustained physical effort under conditions that modern occupational health standards would consider unsafe for extended periods. The Egyptian workers who did this work were not slaves in the simple sense that popular imagination sometimes assumes. The evidence from the Pyramid period, and by extension from the contemporary Red Sea expeditions, suggests a workforce that was fed, housed, and provided with medical care by the state, organized into teams with genuine professional identity and genuine esprit de corps. But they were also doing genuinely hard work in genuinely difficult conditions, and the physical toll of the desert crossing was real, and the organizational challenge of maintaining the health and the morale and the productive capacity of hundreds of workers across a weeks-long desert march was one of the most demanding aspects of expedition management. The officials who managed this, who ensured adequate water and food along the route, who maintained the pace of movement necessary to reach the coast before supplies ran out, who managed the inevitable injuries and illnesses and the various human problems that arise whenever large groups of people undertake demanding physical work together, were among the most skilled administrators in the Egyptian state, and their success in managing the desert crossing was as essential to the expedition's success as the engineering skill of the shipbuilders or the navigational knowledge of the sailors. Reassembly on the coast. The transformation from components to ship. The reassembly of a ship at the Red Sea coast was a moment when the logistical achievement of the desert crossing was transformed into the engineering achievement of the seaworthy vessel. The moment when the individual planks and the rope and the mast sections and the various fittings came together under the hands of the shipwrights into the integrated structure that would carry the expedition across the Red Sea. This reassembly was not simply the reverse of the disassembly that had happened on the Nile side. It was a precision operation requiring the skilled judgment of experienced shipwrights who understood the specific characteristics of each component and the specific way in which it needed to be fitted to its neighbors to produce a hull that was watertight and structurally sound. The mortise-and-tenon joints needed to be fitted carefully, the tenons inserted into the mortises with the right degree of tightness, enough to create a firm connection without splitting the wood, the joints aligned correctly so that the overall shape of the hull was true and the strakes ran fair from bow to stern. The caulking needed to be applied correctly. The fiber and resin mixture worked into the seams with the right consistency and the right pressure, ensuring that the expansion of the caulking when wet would seal the seams without creating pressure that could split the planks. The rope truss needed to be tensioned correctly. The loops of rope connecting bow to stern adjusted to the right tension, enough to counteract the hogging tendency without overstressing the whole structure. The vertical supports amidships positioned correctly to distribute the truss forces across the hull in the intended way. Each of these operations required judgment and skill that could not be fully specified in advance. The kind of tacit knowledge that only comes from direct experience with the specific materials and the specific techniques, from having done this before and learned from the specific ways in which previous assemblies had succeeded or fallen short. The shipwrights who performed the reassembly were therefore not simply following instructions. They were making real-time judgments based on professional knowledge and direct observation of the specific components in front of them, judgments that would determine whether the finished vessel was seaworthy or not. The stakes of getting it right were obvious and immediate. A hull that was not properly assembled would not be discovered to be defective in a safely controlled environment, but in the open water of the Red Sea, where the consequences of structural failure were total and irreversible. The pressure on the shipwrights was therefore genuine, and the quality of their work was genuinely consequential. And the fact that the Egyptian Red Sea expeditions were repeated successfully over more than 1,000 years is a most powerful possible testimony to the consistent quality of the reassembly work that made each voyage possible. The launch, the moment when everything became real. The launch of the reassembled vessel into the Red Sea was a moment when the entire preceding effort, the cedar imported from Lebanon, the planks shaped and jointed in the Nile Valley workshops, the components transported across the eastern desert, the reassembly on the coast, was tested against the reality of the water. A ship that floated, that sat at the correct waterline, that showed no signs of leaking at its seams or flexing excessively at its joints, was a ship that had passed the first and most basic test of the shipwright's walk. But the launch was also a moment of genuine uncertainty, even for experienced shipwrights who had performed the same operation before, because each reassembly was slightly different. Each set of components had its own specific characteristics, and the way in which the assembled hull behaved in the water was not perfectly predictable from the behavior of the components on land. The Egyptian texts and reliefs that document the Punt expeditions do not dwell on this moment of uncertainty. They present the expeditions as straightforwardly successful as the ordered execution of the pharaohs were rather than as a risky, uncertain ventures that they actually were. But the uncertainty was real, and the Egyptians who organized and executed these expeditions knew it was real, and the care and the skill with which they approached every aspect of the preparation, from the selection of the cedar to the tensioning of the rope truss to the application of the caulking, was a response of people who understood that the sea did not forgive carelessness, and who took the preparation of each voyage with the seriousness that this understanding required. The ship is in the water now. The rowers are at their benches, the sailors at their stations, the officers at the stern with the steering oars that will guide the vessel through the coastal waters and out into the open Red Sea. The cargo of supplies for the outward voyage, food and water for the crew, trade goods for the people of Punt, equipment for the journey, is stowed below. The bipod mast is stepped, the sail furled against the yard, ready to be set when the wind conditions allow. And ahead, stretching south and east toward the horizon, is the Red Sea, the volatile, unforgiving, coral-studded, wind-complicated body of water that all the engineering and all the logistics and all the organizational effort of the previous months has been preparation for. The voyage to Punt is about to begin, and the story of what happened on that voyage, the winds and the navigation and the specific challenges of the maritime corridor and the extraordinary destination that waited at the end of it, is waiting in the next segment, patient and ready, for the moment when you are ready to receive it. Let your breathing slow. Let the water rock gently beneath you. The Red Sea is ahead. Segment 4, the voyage, into the unforgiving blue. The ship moved away from the coast. Slowly at first, the rowers working their oars in the careful, measured rhythm of men who understand that the energy they spend now is energy they will need later, that the open water ahead demands a specific kind of physical and mental economy that careless expenditure of effort in the first hours of the voyage will make impossible to maintain. The Red Sea coast of Egypt slides away behind them, the familiar landmarks of the desert cliffs and the harbor installations diminishing with distance until they are small against the enormous scale of the landscape, and then gone entirely, swallowed by the haze and the distance and the specific quality of light that the Red Sea produces in the early morning hours when the sun is still low and the water is still relatively calm. Ahead of them is open water. Not the open water they experience, not the Nile, not the Delta, not the coastal waters they have been navigating in the days since the launch while the crew settled into the rhythms of the ship, and the officers assessed its performance, and the shipwrights made the small adjustments that every newly launched vessel requires. This is different. This is a Red Sea proper, the open corridor of deep water that runs between the African coast to the west and the Arabian Peninsula to the east, narrowing and widening along its length in response to the specific geography of its shores, its surface marked by the specific pattern of waves and swells that the prevailing winds have built up over the fetch of its enclosed waters. The navigator standing at the stern, reading the water ahead with a specific quality of attention that only experience produces, watching the wave patterns, feeling the wind direction on his skin, observing the behavior of the birds above the water and the color of the water itself, is the most important person on the ship at this moment. Not the commander, not the senior priest who has blessed the voyage and whose presence connects it to the divine order that Egyptian civilization understood as governing all significant human undertakings. The navigator, the person who knows this water well enough to keep the ship safe in it. The navigator's knowledge, Reading the Red Sea. The navigational knowledge that Egyptian Red Sea expeditions depended on was not written down in any form that has survived to the modern period. It was oral knowledge, experimental knowledge, the accumulated understanding of specific conditions and specific routes and specific hazards that was built up through repeated voyaging and transmitted through the apprenticeship relationships that connected experienced navigators to the next generation of practitioners. This absence of written navigational records is one of the most significant gaps in our understanding of the Egyptian Red Sea expeditions. We know they made the voyages. We know they reached Punt. We know they returned successfully with extraordinary cargoes. But the specific navigational methods they used, the specific routes they followed, the specific landmarks and the specific celestial references they relied on to maintain their position and their direction, these things are not directly documented in the sources that have survived. What we can reconstruct from the combination of the geographical evidence, the comparative evidence from other ancient maritime traditions operating in similar conditions, and the physical evidence from the expedition sites themselves, is a general picture of the navigational approach that Egyptian Red Sea sailors most likely employed. The primary navigational reference for the outward voyage, heading south and southeast along the coast and then out into open water toward the African coast beyond the Bab el-Mandeb Strait, was the coast itself. Coastal navigation, keeping the land in sight and using the specific features of the coastline as reference points, was the most reliable and the most widely used navigational technique in the ancient world, and the Egyptian Red Sea navigators would have employed it wherever the route permitted, staying close enough to the coast to maintain visual reference while keeping far enough offshore to avoid the coral reefs and the shallow areas that made the coastal waters dangerous. The specific features of the Red Sea coastline that served as navigational landmarks, the distinctive mountains, the specific patterns of coastal indentation and promontory, the specific characteristics of different sections of the coast that experienced navigators learned to recognize, were part of the accumulated knowledge that the navigator carried, built up through previous voyages and transmitted to apprentices through the specific practice of pointing out and naming and explaining the significance of each landmark as it appeared. The celestial references, the sun during the day, the stars at night, provided the directional framework within which the coastal landmarks made sense, the ability to maintain a consistent heading and to recover from navigational uncertainty by reference to the consistent positions of the celestial bodies that the Egyptian astronomical tradition had been tracking and cataloging for millennia. The specific stars that were most useful for Red Sea navigation, the ones whose positions provided the most reliable directional information for the specific routes that the Punt expeditions followed, were among the most carefully observed and most precisely characterized stars in the Egyptian astronomical tradition, and the navigational applications of stellar knowledge were among the most practically important of the many uses to which Egyptian astronomical understanding was put. The Khamsin winds, the enemy that became an ally, the winds of the Red Sea were, as we established in the first segment, the primary environmental challenge that Egyptian Red Sea navigation needed to address, complex, seasonal, organized by the geography of the enclosed sea into patterns that required specific knowledge and specific sailing strategies to exploit effectively. The Khamsin, the hot, dry wind that blows from the south and southwest across Egypt and the Red Sea region during the spring months, carrying dust from the Sahara and producing the characteristic haze that reduces visibility and increases temperatures dramatically, was one of the most challenging weather phenomena that Red Sea sailors encountered. The name Khamsin comes from the Arabic word for 50, reflecting the traditional belief that this wind blows for approximately 50 days during the spring season, a period of genuinely difficult sailing conditions characterized by reduced visibility, strong and gusty wind from directions that complicated navigation, and the physical discomfort of working in hot, dust-laden air for extended periods. For the outward voyage heading south, with the prevailing northerly winds of the Red Sea providing following winds that were broadly favorable for southward movement, The Khamsin presented specific complications, its strong and variable winds adding an element of unpredictability to the otherwise relatively favorable wind conditions of the southward route. The Egyptian sail design, the wide, rectangular sail suspended from a bipod mast, capable of being adjusted in area by reefing and in angle by adjusting the braces that controlled its orientation, was a primary tool through which the ship's officers managed these variable wind conditions, exploiting the favorable periods and reducing sail during the most intense gusts to maintain control and reduce the structural loads on the hull. The skill of the sail handlers, the sailors whose specific job was the management of the sail and the rigging in response to the moment-by-moment changes in wind strength and direction, was therefore one of the most critical competences of the Red Sea crew, requiring the kind of quick, coordinated physical response to changing conditions that only extensive practice and genuine teamwork could produce. But the Khamsin was not simply an obstacle. Experienced navigators understood that the same wind system that created difficulty in some conditions could be exploited in others, that the strong southwesterly winds of the Khamsin season could, at specific moments and in specific locations along the route, provide genuinely useful propulsive force for vessels heading in the right direction. The art of Red Sea navigation was in part the art of reading the wind well enough to exploit its favorable moments while managing its unfavorable ones, of understanding the specific patterns of the Khamsin and the other wind systems of the Red Sea well enough to position the ship correctly for each phase of the voyage, to be in the right place at the right time to catch the wind when it helped and to shelter or adjust when it did not. The coral hazard, navigating the underwater obstacle course. The coral reefs of the Red Sea were not simply a background hazard to be generally avoided. They were a specific, localized, precisely mapped threat that the navigation of the Punt route required detailed knowledge of, the kind of knowledge that could only be acquired through repeated voyaging and careful attention to the relationship between surface conditions and underwater geography. The specific characteristics that made Red Sea coral particularly hazardous for ancient sailors were its proximity to the surface in many locations. Coral heads that reached almost to the waterline, invisible in the specific light conditions that the Red Sea frequently produce, capable of holding a wooden hull with devastating speed and completeness, and its distribution in patterns that were not always predictable from surface observation alone. The navigator's knowledge of the coral, knowing which areas were safe, which required careful threading through specific channels, which were to be avoided entirely in favor of longer routes through deeper water, was therefore not just a matter of general caution but of specific, localized, precisely located information about the specific underwater geography of the specific sections of the route that the expedition followed. This information was accumulated through experience, through the voyages that had gone before, the discoveries made by navigators who had explored the route and noted the hazards, the near misses and the actual groundings that had added to the collective knowledge of where the dangers were and how to avoid them. It was transmitted through the oral tradition of the navigator's craft, through the specific named locations and the specific remembered instructions that experienced navigators passed to their apprentices as part of the practical education that turned a sailor into a navigator capable of taking responsibility for the ship's safety in the specific conditions of the Red Sea. The coral knowledge was proprietary in the deepest sense, not a trade secret in the commercial sense, not something withheld for competitive advantage, but knowledge that was genuinely difficult to acquire, genuinely valuable once acquired, and genuinely dangerous to be without in the specific environment where it was needed. The passage south, day by day on the Red Sea. The voyage from the Egyptian Red Sea coast of Punt was not a quick passage. It was a journey of weeks, perhaps months, through conditions that changed significantly along the route and that required continuous attention and continuous management from every member of the crew. The daily rhythm of the voyage was organized around the specific demands of Red Sea sailing. The morning departure when the winds were typically calmer and the visibility better. The midday period of strong winds and uncomfortable heat that required specific management of the sail and careful attention to the structural behavior of the hull. The afternoon period when the winds often shifted and the sea state changed in ways that required navigational adjustment. The evening arrival at anchorage or the decision to continue sailing through the night when conditions permitted. The crew's physical condition was a constant concern. The combination of physical labor, heat, limited fresh water, and the specific psychological demands of extended voyaging in unfamiliar and genuinely dangerous waters took a toll on the men that the expedition's officers needed to manage carefully. The rationing of fresh water was one of the most critical daily management tasks. The ships carried limited quantities of fresh water in sealed clay vessels, and the rate of consumption needed to be carefully controlled to ensure that the supply lasted until the next opportunity for resupply, either from a coastal water source or from a rain shower, which the Red Sea occasionally produced even in the dry season. The food supply was similarly managed. The specific provisions for the voyage, chosen for their ability to remain edible in the heat of the Red Sea crossing and for their caloric density relative to their weight, were rationed in ways that maintained the crew's physical capacity for work without exhausting the supply before the destination was reached. The maintenance of the ship's structural integrity was an ongoing task. The caulking in the hull seams needed regular inspection and occasional repair as the movement of the hull in the water worked the caulking material and created small gaps that needed to be addressed before they became larger problems. The rope truss needed periodic retensioning as the rope fibers stretched and relaxed in response to the changing loads imposed by the sea conditions, a task that required judgment about the correct tension, too little leaving the hull unsupported against hogging, too much imposing excessive compressive stress on the hull structure. All of this ongoing maintenance and management was the daily work of the Red Sea voyage, the continuous, unglamorous, essential effort that kept the ship safe and functional in conditions that constantly threatened to compromise both. The monsoon reversal, the wind that brought them home. One of the most sophisticated aspects of the Egyptian Punt expedition strategy was the exploitation of the seasonal wind reversal that the monsoon system produced in the southern Red Sea. The shift from the northerly winds that dominated the outward voyage to the southerly winds that periodically appeared during the summer months, providing a natural return wind for vessels heading north. The timing of the expeditions was therefore not arbitrary. It was carefully calculated to exploit this seasonal wind system, departing at the right time to benefit from the northerly winds on the outward voyage and arriving at Punt at the right time to benefit from the southerly winds on the return. This calculation required detailed knowledge of the specific timing of the wind reversals in the specific sections of the Red Sea that the expedition route traversed, knowledge that was as specifically local and as carefully accumulated as the coral knowledge we discussed earlier, and that was equally essential to the practical success of the expeditions. The navigator who understood the wind system well enough to time the voyage correctly was providing the expedition with one of its most valuable assets, the ability to make both legs of the journey with broadly favorable winds, reducing the duration and the difficulty of the voyage and therefore reducing the demands on the crew's physical resources and the ship's consumable supplies. The exploitation of the monsoon reversal was not unique to the Egyptians. Other ancient maritime traditions operating in the Indian Ocean and the Red Sea had developed similar seasonal sailing strategies, but the Egyptian application of it to the specific route and the specific conditions of the Punt expeditions was a genuine achievement of navigational intelligence, the result of careful observation and careful analysis of the relationship between the seasonal calendar and the specific wind. Behavior of the waters they sailed. The ship is moving south now, the coast slipping past to the west, the sun tracking its arc across the brilliant sky above. The crew settled into the rhythms of the open water passage, the watches and the work and the rest and the careful management of water and food, and the ongoing attention to the behavior of the hull beneath them. The Red Sea is everything it was described as: volatile, demanding, unforgiving of mistakes, beautiful in its specific way, the specific beauty of a genuinely wild and powerful natural environment that does not accommodate human weakness. But the ship is holding. The cedar planks are bearing the loads of the open water with the specific resilience that the mortise-and-tenon joints and the rope truss and the sewn hull were designed to provide. The sail is drawing well in the conditions of the morning wind, the bipod mast standing firm against the forces the sail transmits to the hull. The steering oars maintaining the heading of the navigator has determined will carry the expedition toward its destination. And somewhere ahead, south and east, beyond the horizon, beyond the stretch of open water that the crew can see from the deck, beyond the sections of the route that are still to come, Punt is waiting. With its gold and its ebony and its incense trees and its extraordinary abundance of the things that Egypt needed, and that the Red Sea was the only path to reach. Let your body be heavy now, and let the ship carry you, and let the night air of the Red Sea settle around you, warm and salt-scented and alive with the specific sounds of an ancient vessel moving through open water, the creak of the hull, the whisper of the sail, the steady rhythm of the water against the cedar planks. The destination is close. The story of what they found there and the extraordinary challenge of bringing it home is waiting in the final segment. Let your breathing slow. Let the Red Sea rock you gently. Almost there. Segment 5, Punt, the cargo, and the voyage home. The land appears on the horizon slowly, not dramatically, not the sudden revelation of a coastline emerging from fog the way European maritime mythology sometimes described the appearance of land after a long ocean crossing, but gradually, the way land always appears when you have been watching for it carefully and when the conditions of visibility are good and the navigator has placed the ship on the correct heading to make the landfall at the right point. First, a darkening of the horizon, a slight thickening of the line between the sea and the sky that experienced eyes know how to read as the presence of land rather than cloud. Then the specific shapes of the coastal hills, emerging slowly from a haze as the distance closes, becoming more distinct and more recognizable as the features that the navigator has been looking for, the landmarks that confirm this is the right place, that the crossing has been made correctly, that the weeks of navigation across the volatile Red Sea corridor have brought the expedition to exactly the destination that the pharaohs order specified. And then the smell. Before the details of the coast are fully visible, before the specific features of the Punt shoreline can be clearly made out, the smell reaches a ship, the extraordinary, complex, resinous fragrance of the incense trees that made Punt famous across the ancient world, carried out to sea on the offshore breeze, unmistakable to anyone who had been there before and unforgettable to anyone who was making the crossing for the first time. The smell of Punt was a smell of frankincense and myrrh and the other aromatic resins that the trees of this coast produce in abundance, resins that were among the most valued commodities in the entire ancient world, burned in the temples of every major religion from Egypt to Mesopotamia to the Levant, traded across thousands of miles of land and sea routes, worth their weight in silver in the markets of the ancient Near East. The ship that was carrying the expedition to Punt was carrying, in its hold, the trade goods that would be exchanged for these resins and for everything else that Punt offered. And the exchange that was about to take place was one of the most important commercial transactions in the ancient Egyptian economy. The specific result that all the engineering and all the logistics and all the navigation of the preceding weeks and months had been in service of. Punt, what it was and why it mattered. The location of Punt has been one of the most debated questions in Egyptology for more than a century. The ancient Egyptian texts describe it as a real place, clearly located somewhere accessible by Red Sea voyage, but the specific identification of its location in modern geographical terms has been the subject of considerable scholarly argument. The current consensus, based on the combination of the geographical evidence in the Egyptian texts, the botanical and zoological evidence in the reliefs that depict the products of Punt, and the archaeological evidence from sites along the East African and Arabian coasts, places Punt in the region of what is now Eritrea, Djibouti, Somalia, and possibly extending into the adjacent parts of the Arabian Peninsula. This region, the area around the southern end of the Red Sea and the northern Horn of Africa, is consistent with the product that the Egyptian text described Punt as producing, consistent with the sailing times of the voyage account suggests, and consistent with the specific geographical features that the release of Deir el-Bahari depict as characteristic of the Punt landscape. Punt was not a single unified polity in the sense of a state with clearly defined borders and a centralized government. It was more likely a region, possibly with multiple political entities, united in the Egyptian conceptualization by its geographical location and its characteristic products rather than by any political unity that its own inhabitants would have recognized. The Egyptians had been aware of Punt for longer than the specific documented expedition suggests. References to it appear in Egyptian texts from the Old Kingdom period, and the specific familiarity with which later texts discuss it implies a relationship that had been established and maintained over centuries rather than the product of a single dramatic discovery. Punt was, in the Egyptian geographical imagination, one of the most significant places in the world. Not because of its political power, not because of its military strength, not because of any cultural achievement that the Egyptians particularly admired, but because of what it produced, the specific natural abundance of the place that made it uniquely valuable to a civilization that needed what it had and could not obtain it from anywhere closer. The product to Punt, what the journey was for. The cargo that the Punt expeditions brought back to Egypt was not a single commodity but a carefully assembled collection of specific products, each one valued for specific reasons, each one serving specific functions in the Egyptian economy and the Egyptian ceremonial and religious life that the economy supported. Myrrh resin was perhaps the most important single product. The dried sap of the conifer trees that grew along the Punt coast, used extensively in Egyptian religious ritual as incense burned in temple ceremonies, as an ingredient in the complex preparations used in mummification, and as a component of the aromatic oils used in the anointing of the dead and the living in various ceremonial contexts. The demand for myrrh in Egypt was consistent and substantial. The temple ceremonies that consumed or performed daily across the hundreds of temples that studded the Egyptian landscape, and the quantities required to maintain this continuous ritual activity was significant enough that the supply from local or nearby sources was insufficient, making the Punt expeditions a necessary component of the religious economy of the Egyptian state. Frankincense, the resin of the boswellia trees, distinct from myrrh but equally valued for its aromatic properties, was similarly important. Its specific fragrance associated with the presence of the divine in Egyptian religious understanding. Its burning in the inner sanctuaries of the temples, a constant feature of the ritual activities that maintained the relationship between the human world and the gods. Ebony, the dense, fine-grained blackwood of the Diospyros trees that grew in the forests of East Africa, was one of the most valued luxury materials in the ancient Egyptian economy, used for the finest furniture, for the construction of statues, for the handles of tools and weapons that were intended for ceremonial use rather than purely practical purposes. The specific properties of ebony, its extraordinary density and hardness, its ability to take a high polish that produced a surface of almost mirror-like reflectivity, its deep black color that made it visually striking in combination with the gold and ivory that were the other primary luxury materials of Egyptian decorative arts, made it irreplaceable for specific high-value applications that no substitute material could adequately serve. Gold was present among the Punt products as well. Not the West African gold that funded the medieval empires we discussed in an earlier story, but the gold of the East African region, obtained through the same trade networks that supplied the other Punt products, adding to the Egyptian treasury's reserves in ways that supported the broader economy of the empire. But the most extraordinary product of the Punt expeditions, the one that is most vividly depicted in the Hatshepsut reliefs, and that represents the most ambitious and most logistically challenging aspect of the cargo, was the living incense trees. The living trees, the most ambitious cargo in ancient history. The reliefs at Deir el-Bahari that document the Punt expedition of Hatshepsut the most extensively depicted and most thoroughly documented of all the Punt expeditions. So, among the cargo being loaded onto the Egyptian ships, a sight that is genuinely extraordinary even by the standards of ambitious ancient logistics. Living trees, not dried timber, not processed wood, not botanical specimen preserved in some form that made them easy to transport, but living, rooted, soil-encased incense trees, their root balls wrapped and protected for the voyage, their branches intact, their capacity for continued growth and continued resin production preserved through the extraordinary care of the people responsible for their transport. The ambition of this is almost breathtaking. Loading live trees onto ancient wooden ships, maintaining their viability through weeks of maritime transport in the specific conditions of the Red Sea, and delivering them to Egypt in a condition that allowed them to be transplanted successfully and to continue growing in their new environment. This was not simply an impressive logistical achievement. It was a genuinely novel one, an attempt to do something that had not been done before and for which no established protocol existed. The motivation for this ambition was clear. If living incense trees could be successfully transplanted to Egypt, the constant demand for their products could be met without the expense and the risk of repeated Red Sea expeditions. The supply chain for one of the most essential commodities in the Egyptian ceremonial economy could be secured domestically rather than depending on the treacherous maritime connection to Punt. Whether this ambition was fully realized, whether the transplanted trees actually survived and produced resin in their Egyptian setting, is not definitively established by the surviving evidence. The reliefs show the trees being planted in the garden of Hatshepsut's temple at Deir el-Bahri, and some Egyptian texts reference incense trees growing in Egypt, suggesting that at least some degree of successful transplantation was achieved. But the specific climate of Egypt, drier and hotter than the East African coast, with different soil conditions and different patterns of rainfall, was not ideal for the incense trees, and it is likely that the Egyptian plantings were never fully self-sustaining, never completely replacing the need for continued Punt expeditions to supply the ongoing demand for myrrh and frankincense. The attempt itself, regardless of its ultimate success, is one of the most remarkable examples of ancient botanical ambition. The effort to transfer not just a product of a distant ecosystem, but the living system itself, to relocate the source of supply rather than simply continuing to travel to the source. Loading the cargo, the engineering of abundance. The loading of the Punt cargo onto the Egyptian ships was an engineering challenge of its own, matching the extraordinary abundance of what was being taken aboard with the specific structural capacity of vessels that had been designed for the crossing, and that now needed to carry a retained cargo of extraordinary weight and volume. The Hatshepsut reliefs show the loading process in considerable detail, the organization of the workers, the specific methods used to move heavy cargo from the shore to the ship, the way in which the living trees and their wrapped root balls were handled and stowed, the organization of the gold and the resins and the ebony in the ship's hold. The weight management of the return cargo was a critical concern. The ships needed to be loaded to a draft that was safe for the Red Sea crossing, deep enough to provide stability in the wave conditions of the open water while not so deep that the hull was unnecessarily stressed or the freeboard reduced to a level that made the vessel vulnerable to taking water over the sides in rough conditions. The experienced officers who managed the loading were making continuous judgments about the distribution of weight across the hull, ensuring that the cargo was not concentrated in ways that created dangerous stress concentrations, that the trim of the vessel was maintained in the fore and aft direction so that the steering remained effective, that the living trees were positioned in ways that minimized the movement of their weight as the ship moved in the seaway. These were not simple calculations. They were the practical application of an intuitive understanding of ship behavior that the officers had developed through years of experience, the same tacit knowledge that governed every other aspect of the Red Sea voyage, but applied now to the specific challenge of loading and managing a cargo of unusual weight and unusual character. The return voyage, heavier, slower, more dangerous. The return voyage from Punt to the Egyptian Red Sea coast was in many respects more demanding than the outward voyage. The ships were now carrying the full weight of the Punt cargo, sitting deeper in the water, moving more slowly, responding more sluggishly to the helm and to the wind, their structural members under greater stress from the additional weight they were bearing. The hull's hogging tendency, the tendency of the heavily loaded hull to sag in the middle under the weight of the cargo, was more pronounced than on the outward voyage, and the rope truss needed to be retensioned to compensate. The additional tension in the rope adjusted carefully to counteract the increased hogging force without overstressing the hull structure. The caulking in the hull seams was under greater stress from the deeper draft, more water pressure on the external surface of the planks, more tendency for the seams to work open as a hull flex in the wave action of the return crossing. The regular inspection and maintenance of the caulking was therefore even more critical on the return voyage than it had been on the outward one. The consequences of a hull leak in a ship carrying the full weight of the Punt cargo far from any harbor, in conditions of the open Red Sea, were too serious to allow any laxity in the maintenance routine. The seasonal wind system that the expedition timing had been designed to exploit was a crucial advantage on the return. The southerly winds of the summer monsoon season providing the following wind that made the northward passage manageable in a way that would have been extremely difficult or impossible against the prevailing northerly winds that dominated the Red Sea for most of the year. The navigator's knowledge of the wind timing was therefore one of the most critical factors in the success of the return voyage. The ability to identify the specific window of southerly winds and to position the ship correctly to exploit it was a difference between a manageable return passage and an agonizing struggle against contrary winds in an overloaded ship. The arrival, what it meant for Egypt. The return of a Punt expedition to the Egyptian Red Sea coast was not a quiet event. It was a culmination of months of preparation and weeks of dangerous maritime travel, the successful conclusion of one of the most ambitious commercial and logistical undertakings that the Egyptian state regularly organized, and its arrival was marked with the ceremony and the celebration that its significance deserved. The unloading of the cargo, the gold and the myrrh and the frankincense and the ebony and the living trees and the various other products that had survived the crossing, was itself a ceremonial event. The products counted and catalogued and formally presented to the officials who would record them in the state accounts and distribute them to the temples and the palace storerooms where they were needed. The Hatshepsut reliefs at Deir el-Bahari conclude their depiction of the Punt expedition with exactly this scene. The formal presentation of the Punt cargo to the pharaoh, the counting, and the weighing and the recording that transformed the product of the voyage from raw expedition cargo into the formally accounted resources of the Egyptian state. It is a scene of genuine triumph, the satisfaction of a difficult and dangerous undertaking successfully completed, the vindication of the engineering and the logistics and the navigation that had made it possible, the proof that the Red Sea, for all its volatility and all its dangers, could be crossed and recrossed by Egyptian ships carrying Egyptian sailors in service of the Egyptian state's needs. And behind this scene of triumph, visible in the architectural context of the reliefs, in the temple whose walls they decorate, in the specific religious and political purposes that the Punt expedition served in the context of Hatshepsut's reign, is a deeper significance of the achievement. The Punt expeditions were not simply commercial ventures, not simply supply operations to obtain commodities that Egypt needed. They were expressions of Egyptian power and Egyptian capability, demonstrations that the civilization that had built the pyramids and organized the Nile Valley into the most productive agricultural system in the ancient world could also organize the crossing of the Red Sea and the extraction of its extraordinary resources. They were statements about what Egypt was, about the reach of its organization, the capability of its engineering, the skill of its sailors and its shipbuilders and its navigators, the ambition of its rulers who looked at the Red Sea and saw not an obstacle but an opportunity. What they left behind. The Egyptian Red Sea shipbuilding tradition did not simply produce ships and voyages. It produced knowledge, accumulated over centuries of practice and preserved in the specific tacit understanding of the craftspeople and the navigators and the officials who organized and executed the expeditions. This knowledge influenced the maritime traditions of the Red Sea and the Indian Ocean long after the specific political entity of the Egyptian state had ceased to organize Punt expeditions. The specific techniques of shell-first construction, the mortise-and-tenon joinery, the sewn hull, the rope truss, all of these spread through the maritime networks of the ancient world, adopted and adapted by the various seafaring peoples of the Indian Ocean basin in ways that shaped the development of maritime technology in the region for centuries. The dhow traditions of the Arabian Sea and the Indian Ocean, the sewn plank vessels that were the primary form of ocean-going transport in the Western Indian Ocean for millennia, are in some respect the descendants of the Egyptian Red Sea shipbuilding tradition, their specific construction techniques echoing the same fundamental principles that the Egyptian shipbuilders developed for the specific demands of the Red Sea environment. The knowledge that the Egyptians created, through the specific, demanding, practically grounded process of solving the engineering problems of Red Sea shipbuilding, became part of the broader maritime knowledge of the ancient world, contributing to the development of the tradition that would eventually produce the ships of the Indian Ocean trade, the vessels that connected East Africa and Arabia and India and Southeast Asia into the most extensive maritime trading network of the pre-modern world. Let your body grow completely heavy now, the full settled weight of a body that has traveled a long way tonight, across the eastern desert with the ship components on the backs of Egyptian workers, across the Red Sea with the navigator watching the coral and the wind, through the extraordinary environment of Punt and back again with a cargo of incense trees and myrrh and gold and ebony. You have been on the water tonight, in the dark of the Red Sea, feeling the cedar planks beneath you and the rope truss above you, smelling the salt air and the incense that was already beginning to drift from the Punt cargo in the hold. You have been in the hands of the shipbuilders and the navigators and the sailors and the officials and the workers who made the whole thing possible, the people whose specific knowledge and specific skill and specific commitment to the demands of the task were the real substance of the achievement, more important than any individual piece of technology or any specific organizational decision. Let all of it settle into you now, quietly and completely, the way the sea settles after the storm, finding its level, returning to its natural state, the surface smoothing out over the deep water that was always there beneath the turbulence. The Red Sea is calm tonight. The ships are safe in the harbor. The cargo is unloaded and counted and formally presented to the officials who will record it in the state accounts of the most organized civilization in the ancient world. And somewhere in the garden of Hatshepsut's temple at Deir el-Bahri, in the warm Egyptian night, the incense trees that were carried across the Red Sea in the hold of an Egyptian ship are standing in their transplanted soil, their roots reaching down into Egyptian earth for the first time, their branches carrying the extraordinary fragrance of Punt into the night air of a country that is not their home but that needed them enough to cross one of the most dangerous bodies of water in the ancient world to bring them here. Let your eyes be heavy now. Let your breath be slow. The cedar and the rope held. The navigator found a way. The cargo came home. And tonight, in the quiet of this particular hour, you know how. You know the mortise and the tenon and the rope truss and the sewn hull and the bipod mast and the wide rectangular sail and the seasonal winds and the coral hazard and the eastern desert route and the modular design that made the crossing possible. You know the names of the things that kept the ship together and the knowledge that kept the sailors safe and the organizational intelligence that turned the impossible into the routine. Let it rest in you now, gently, completely. The Red Sea is behind you. The night is ahead, and the night is calm and warm and full of the particular peace that comes after something difficult has been successfully done. Let your breathing carry you down, into the deep, into the quiet, into the rest that is waiting for you on the other side of this long and extraordinary night. Good night.